As mentioned in the earlier lecture, soluble materials give gaseous films, and surface active agents are a very good example, since they are sufficiently dilute and hence have negligible solute-solute interactions at the surface. Therefore, they cause a linear lowering of surface tension gamma. That means gamma is equal to gamma naught minus Bc, where B is a constant, or gamma naught minus gamma is equal to Bc. If we differentiate this with respect to C, we get the gamma by dc being equal to minus B. If we then substitute this into Gibbs equation in the form of capital gamma is equal to minus C, the gamma by dc kt will then become capital gamma is equal to 1 over A, where A is area, which is equal to Bc over kt, which is equal to pi over kt, or pi A is equal to kt. A is the average area per molecule. It's found that CTAB, cetyl-to-methyl ammonium bromide, gives a very good example of gaseous films. You can see this in CHE442, page 1044, fourth edition, a little bit further for other editions. Let us look at condensed films. These are exhibited by palmitic, stearic, and higher chain fatty acids at room temperature. In these, molecules are in clusters because cohesion between the molecules is much greater than adhesion between the molecules and the interface. As seen in the diagram here of pi against A, for dilute HCl we have that curve, whereas on pure water we have that curve, which is very steep. Here are some real examples of pi A curves for oleic acid on water at 20 degrees C. Once again, it's pi in millinewtons per meter against A in nanometers squared per molecule. As you can see, it is quite steep that way. Similarly, pi A curves for stearic acid sprayed on water and on dilute acid at 20 is given by this diagram. On pure water, as we said before, is that steep one, and on dilute HCl is that. You can see that the steep one, if extrapolated to 0 pi, will give you an area per molecule there. A schematic representation of the pi A curves for myristic acid spread on 0.1 moles per decimeter cubed HCl at 14 degrees centigrade is of interest. Once again, it's spreading tension pi millinewtons per meter against area per molecule. We see that at very high areas per molecule, the curve is very similar to a gaseous hyperbolic curves. But as we reduce the area per molecule, we get one where we literally have no slope. and that is sometimes called the transition, because the next one has a slope with higher magnitude of the slope, and this is similar to the liquid expanded system we mentioned earlier. If we move a bit further, we get another transition, which then gives us the condensed molecular behavior. Let us look at expanded films again. Here, an example is oleic acid. Now, oleic acid has got a double bond within it. It has a more expanded film than stearic acid. The double bond allows less cohesion between hydrocarbon chains. It also has greater affinity for water. On compression, molecules take up a vertical position, as we saw before. Now, the pi A curves are similar to those of PV curves in 3 dimensions, as mentioned earlier. Myristic acid displays all the different film states, as we saw in the diagram before, and obeys a gas law similar to the van der Waals equation. That is, pi minus pi naught in brackets into A minus A naught in brackets is equal to KT. On your own, you should look at the factors affecting the physical state of monolayer films. What are the applications of these surface films? We live in a desert in this country, Botswana. Consequently, surface films are very useful to us because we can use them to conserve water. In mines, we can also use them to protect water droplets which trap dust. For example, in the underground mine at Morupule, where coal is mined, there's a lot of dust. So water has to be spread in order to trap these dusts, otherwise it becomes very unhealthy for the miners. We can actually use this method to determine molecular masses of proteins and in the interpretation of anomalous results. In this view, look at the interaction in mixed layers and on biological membranes.